Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce what I call the thermodynamic variables here. And what we're looking at is we've got this piston cylinder assembly and all these different colored dots here. These dots represent some sort of gas molecules contained within this container. Now, some things to consider here. Well, one, why are there different colors? Well, if you were to take a sample of, say, air, it's got some oxygen and nitrogen and some other things. So, a typical sample of gas has many different molecules present. Some other things to consider, I've drawn, I don't know, maybe 30 dots here just for visualization purposes. The actual number of molecules in the container, these are unfathomable numbers. These are numbers like, 10 to the 24th power. Other things to consider, here I drew the dots so that we could see them. You can't see air molecules. They're many times too small to see. But again, just for visualization purposes, I think that it's nice to have these present. Now, there are three thermodynamic variables that are extremely important for gases. There's other variables that we'll be talking about, but for now we're going to talk about these three. And those are volume, pressure, and temperature. Volume is just like you might think. It's the same volume. You measure milk typically by volume or gasoline or whatnot. The standard units for volume in physics typically is the cubic meter, but sometimes we'll use things like liters, cubic centimeters, etc. All right, we're going to talk a little bit about pressure now, where that's coming from. So if you imagine ourselves inside this container here, and if I picked one of these molecules, like this guy right here, these things are moving along pretty fast. Typical molecular speeds here, these are measured in thousands of meters per second. And if I were to track one of these particles, the motion would be highly chaotic. This one particle might just move all over the place. But every once in a while here, it's going to hit this wall and bounce back. All right? And other molecules also hitting this wall and bouncing back. So if I think about what's happening at this surface here, every once in a while, a molecule is hitting it and recoiling. And when I say every once in a while, this is happening like 10 to the 30th times per second. There's just almost an infinite number of impacts here. So if we think about what that's doing to the piston, I'm going to do kind of a cut and paste here. Every time a molecule hits this piston, the molecule rebounds and the molecule's momentum changes. And that's because there's an impulse exerted between the molecule and this wall. That impulse is left on the molecule. It's to the right on this wall. So if I put a little impulse here for one of them, a little F delta T, and I'm actually just going to put an F here. The only difference between the F and the impulse would be the time factor. And remember that this is happening like 10 to the 30th times per second. So there's all kinds of these, more than we could ever draw or imagine. And then if we added these all up, these would add to one single force vector. I'm going to go ahead and put F total here or something. Pressure is defined as force per unit area. If I took the total force vector acting on this and divided by the total area along this surface, I would get what is called the pressure in the container. So the units of pressure, the standard unit in physics would be the Newton per square meter. The English unit, let's see, the pound per square inch is used quite often, or maybe pound per square foot. It's important to realize what's physically causing the pressure, and the answer to that is molecular impacts. The molecules hitting the walls of the container everywhere. Or if I were to put an object inside of here, the molecules will be hitting all faces of this, effectively trying to compress it. So that's what pressure is. It's force per unit area. There's a very important thing to understand about the pressure numerically. One way I could decrease the pressure is if I perhaps, put a valve here or something and somehow removed some of the molecules in the container. If I were to remove some of the molecules in the container, there would be fewer impacts per second, and the net force would go down, and therefore the pressure would decrease. If I removed more molecules, there's fewer impacts, and again the force is going down, and again the pressure is going down. The million-dollar question is, how many could I remove? Well, the answer is all of them. If I were to remove all of the molecules in this container somehow, now don't worry about the how, just focus on what if we did. Somehow closed our valve again, and we ask ourselves how many molecules are hitting this surface. The answer now is 0. There's no impacts, no impulse is exerted on this piston on this side, and therefore the pressure in the container would be 0. Now the million-dollar question is, can we go lower than that? And the $1,001 answer is no. We can drop the pressure by removing molecules, but once they're all gone, that's it. We can't drop any lower than none. So pressure actually has a bottom value to it, and that value is 0. All pressures are in fact positive quantities, and the lowest possible pressure would be a pressure of 0, and that's it. Can't get any lower than that. So really, in theory, pressures are always positive. Now, for anybody watching this video, there's a good chance that you've used a gauge and measured a pressure that was negative. Well, that's because when we take a pressure measurement, we normally are taking a measurement with respect to 1 atmosphere of pressure. If you're watching this video, it's very likely that you are somewhere on the surface of the Earth, and the surface of the Earth has what's called atmospheric pressure. And the atmospheric pressure is about 14.7 psi, or pounds per square inch. This varies, maybe by 5% or so, maybe even 10%, depending on where you're at. But this is a pretty good average at sea level. I like to just approximate that to 15 psi for this discussion that we're about to have. In newtons per square meter, that's about approximately 10 to the 5th newton per square meter, or about 10 to the 5th pascals. A pascal is defined as a newton per square meter, so these are the same thing. So imagine that you're sitting in a classroom with me and you're talking about pressure measurements, and imagine that somebody could somehow seal the room off. Now, while we're having this discussion, atmospheric pressure is about 15 psi. If we were to take a gauge and read it in that environment, it would read 0. So there's something to realize. We've got two different pressures we're talking about now. We're talking about absolute pressure and gauge pressure. So within this room right now, we would say that the gauge is reading 0. The absolute pressure is about 15 psi. I'll put the units off to the left. If we were to somehow remove some of the air from the room and drop the pressure by 5, the absolute pressure would now be about 10 psi. The gauge would now read minus 5 psi. So you can have a negative pressure on a gauge. Or a gauge pressure can be negative. That's just because the 0's been moved. If we drop the pressure by another 5, the absolute pressure is now 5 psi. The gauge is now reading minus 10. Now, we would not, if we actually did this and we were in the room, we would not be happy. This would have all sorts of bad problems on your health, but again, it's just a theoretical example. If we drop it by another 5, the absolute pressure would now be 0. The gauge is now reading minus 15 psi. So you can have a gauge pressures that are negative. The negative pressures just mean below atmospheric pressure. That's sometimes, or not sometimes, but that's referred to as a vacuum situation. And we can't get any lower than this, right? Because we can't drop that pressure anymore. Once all the molecules are out of the room, that's it. We can't remove more than, we can't remove any more molecules from 0. So, again, the lowest possible gauge pressure is about minus 15 psi. I say about because atmospheric pressure here is 14.7. I rounded for the example of the discussion. So pressures are force per unit area, so they're measured in Newton per square meter. You've got two types of pressure. You have to always know which one you're dealing with. There's gauge pressure and absolute pressure. I like to call the absolute pressure the true pressure. Absolute pressures are always positive. They have to be because of how they're defined. Gauge pressures can be negative if you have a vacuum type of situation. Standard units, let's see, Newton per square meter, or typically pound per square inch. I forgot the square on that inch. So that's enough for our pressure measurement. Now I'm going to talk a little bit about temperature. So I'm going to get rid of this stuff. All right, so getting back to our container here, whoops, that had a bunch of molecules in it. And I probably won't get them all back, but let's see here, and some pretty green ones here for Christmas coming up. All right. Then we're going to talk a little bit about our temperature now. So temperature is a measure of molecular kinetic energy. So each of these molecules, again, they're moving pretty fast. It's not uncommon at all for these to be moving at speeds measured in thousands of meters per second. Temperature is a measure of molecular kinetic energy. And remember that kinetic energy is calculated by 1/2 mv squared. So basically, this allows us to say that a temperature measurement is a number that is directly proportional to the average molecular kinetic energy of the molecules in this container. So basically, it's a measurement of molecular speed because kinetic energy is 1/2 mv squared. So when something has a high temperature, that means its molecules are moving very, very, very fast. And when its temperature is lower, it means the molecules are moving very, very, very slow. Also, because of how it's calculated, kinetic energy is always greater than zero. These things are always positive. You can't have a negative kinetic energy. That puts a bottom floor to a temperature measurement. Temperature measurements are always greater than zero. Now, you might wonder about, well, what about equality here? Well, in theory here, a temperature equal to zero, and I mean identically equal to zero, is called absolute zero. That's what it's actually named. It is the theoretical floor, the theoretical lowest temperature that could ever be measured. To my knowledge, nobody has ever cooled anything down to absolute zero. People have gotten really, really, really close. I'm not sure how many decimals. I'll have to go back maybe and look that up. But to my knowledge, every temperature measurement that's ever been done was greater than zero. Absolute zero is a theoretical maximum, and I don't know, maybe it'll be reached someday. I don't know. At this point where I'm making this video, I do not believe it has. People have gotten close, 0.000, I'm not sure how many zeros, but nobody, I think, has actually cooled something to identically zero. Absolute temperatures are measured by quantities called the Kelvin. So absolute zero would be 0 kelvins. Now, the Kelvin scale is the what I call the true temperature scale, but that's not the most common scale used. Probably the most common temperature scale used is the Centigrade scale, or what's sometimes called the Celsius scale. The Centigrade scale is based on water, and it's based on the phase change temperatures of water. The temperature at which water freezes, I'll put the freezing point of H2O, is defined to be 0 degrees centigrade. And then the boiling temperature of water, I'll put the boiling point, that's the temperature at which water changes from liquid to a gas, is defined as 100 degrees centigrade. Actually, this needs to read right to left. 0 degrees centigrade is defined as the freezing point of water, or the temperature at which water freezes. 100 degrees centigrade is defined as the boiling temperature of water, or the temperature at which water boils or changes phase from a liquid to a gas. And obviously there's 100 divisions in between. One of the things that happens quite commonly, we need to be able to go back and forth between the centigrade scale and the Kelvin scale. It's important to realize it's not a proportional relationship between them, it's a linear relationship. Your temperature in kelvins is equal to your temperature in centigrade plus 273.15. Let me just make sure. 0 minus, yeah, that's it. I usually just use the 273. I don't know that the 15's necessarily needed. And to go through some kind of samples here, so if I were to talk about absolute 0 kelvins, and if I solve that for the temperature in centigrade, you would get minus 273.15 degrees. So minus 273.15 centigrade would correspond to absolute 0. The freezing point of water would be 0 degrees centigrade. That would be 273 kelvins. The boiling point of water would be 100 degrees centigrade. This would be 100, and that would then therefore be 373 kelvins. Some language here. Usually when you're talking centigrade, it reads degrees centigrade. It's not actually, when you give a Kelvin temperature, it's not degrees Kelvin, it's just said kelvins. So for example, the freezing point of water would be 0 degrees centigrade. You'd put a 0 here. Numerically, that's 273 kelvins, not degrees Kelvin. So again, it's a linear relationship going back and forth. It's not a conversion factor because they're not proportional. Also notice if I go up 1 degree centigrade, you go up exactly 1 degree Kelvin. So this is a very important fact of life and science. Delta T in centigrade is exactly equal to a delta T in kelvins, and that will show up from time to time. So anyway, the purpose of this video was to introduce volume, pressure, and temperature. I think that I've gotten all three of those done, so I think I'll just end that here. I hope anybody watching this has gotten something out of it. Have a great day.